Hello everyone, I'm Siyang Yuan. I'm glad to present our work Learning to Weight Filter Groups for Robust Classification. I work with Yitong, Dong, Becky, Larry, and Davey on this project. First, about the task. In this work, we focus on domain generalization task, which considers how to take knowledge acquired from an arbitrary number of related domains and apply it to previous unseen domains. Here is an example of classic benchmark PACS. In this example, the data with labels of domain photo, art painting, and cartoon are available during training, and the model is evaluated with the unseen sketch domain. The model is expected to shift knowledge learned from training domains to the unseen domain and address domain gap. In our proposed method, we allow each domain to have both shared and unique properties, while explicitly encourage domain generalization during training and address the domain gap. Specifically, we propose the domain-specific filter groups DSFG approach. In our approach, each training domain has a unique filter group, and each test data point is predicted by a weighted sum over the outputs of different domain filters. It also has a separate neural network, learns to estimate the appropriate filter group weights through a meta-learning strategy. Empirically, we show experimental results on 3 benchmark datasets, demonstrate improved performance compared to current state-of-the-art approaches. Here is our model framework. The key component of DSFG is the FConf layer, which has both shared and domain-specific filter groups. The shared filter group learns common representations, while the domain-specific filter groups are focused on their own domains. We use a type of channel attention mechanism and the weight generator here to generate weights to combine the output of each filter banks by a weighted sum to generate output of FConf layer. The goal guiding the training process is to perform well on an unseen test sample without further model parameter updates. This first requires that the shared and domain-specific filter groups perform well on the known source samples. Furthermore, the weight generator should assign filter weights for each data point to enhance generalization. We use in-domain and cross-domain training and weight generator update processes to encourage these properties. In-domain training, where data in domain S only uses the shared filters and its domain-specific filters to make prediction. In this step, filters are learned that perform well on the existing domains. For cross-domain training, which emphasizes learning how to generalize to new samples by mimicking test procedure, we optimize the classification loss using a weighted combination of all available filters. And during weight generator updates, we use a combination of cross-domain objective, prior loss, which encourage self-similarity, and entropy loss to prevent it to collapse to a specific filter group as the objective function. And we use meta-learning update scheme to give accurate filter weights and encourage high label classification accuracy by bridging the in-domain and cross-domain training losses in the gradient space. The whole training framework iteratively conducts in-domain training, cross-domain training, and weight generator updates. Here is our experimental results on PACS dataset. Our method achieves better or comparable performance compared to state-of-the-art models on all of the domains. This suggests that our model is robust and can improve the prediction accuracy even when the domain gap is large and the network is deep. And the meta-learning step provides improvements. Thanks for listening. If you're interested, we have a lot more detail and experimentation in our manuscript.